Okay, welcome back to the fifth and final part in this five-part series on calculating the critical t-value. In this last section, I just want to explain some connections to various numerical sequences, as well as go over some of the philosophical points that I was hitting on earlier, just to round things off. So, if we remember, the motivation for doing this had to do with this general problem of generalizing from experience, which is to say, inferring global statistics given our measure of local statistics. And this problem crops up in all kinds of places, but the one example I used to elaborate why this is important has to do with the upper confidence level. And if you remember, we were trying to determine whether or not, or to what degree, we can be confident our sample mean and sample variance are good reflections of the population mean and variance, and to try and bound the confidence with which we could ascribe our locally measured statistics with regards to the true statistics. So again, when we assumed that the population mean or the population was distributed according to a normal distribution, we were able to derive the t-statistic and the critical t-value, which enabled us to bound, to put a number on how confident we could be that our local measure, our random subsample, and measure of the sample mean, whether that was a good stand-in, and to what degree we could be confident that that was a good stand-in for the global mean, or the global, or statistics on the global distribution, the population distribution. So philosophically, this crops up in a lot of different places, and it's nice to know that once you get to the end of all this heady mathematics, that there is a nice, neat, analytical representation formula to help you in deriving that quantity. And this was the value we came up with for the critical t statistic, with a one-tail confidence interval of 1 minus 2 times eta and v degrees of freedom. And if you actually use this program described by Dominici to calculate terms of this sequence, you get an interesting result, and that's exactly what I've done here. In MATLAB, I coded up a few of these just to see what the polynomials look like, and as far as I can tell, these polynomials are new, or they don't have a representation, as far as I can tell. No closed form formula, with the exception of that given by Dominici. But they are quite interesting, and here I've calculated a number of them up to the 16th operator, and you'll notice that there are no odd values for the operation. That's because on each odd value of the operation, you get a value of 0, and so those go away, and all you're left with are these even values of the operation and these interesting polynomial sequences, integer polynomial sequences of numbers. So I wanted to rewrite the formula to reflect the fact that you can skip calculating odd values of the Dominici terms. And here I've done that. So this is just re-saying the same thing. It's another way of looking at the critical t value for v degrees of freedom. And here I've just gotten rid of those odd valued terms. In this sequence, I used to calculate various values and compare them to what is sort of given in your Buck standard t-table. The first value of which I calculate for a one-tail value of 0.15, which and 3 degrees of freedom, which is this value here. And you notice that that would give me an 85% confidence interval, and the value given in the table is 1.25, and the value that 16 terms of that expansion will give you is very close. It's 1.249, and if you round it up, you would get the answer given by the table. The second term is 10 degrees of freedom, and you can see it right there on the right, with a 75% confidence and 10 degrees of freedom. I get 0.6998, comparing that to the book value, so to speak. We're very close. We're within two, let's see, what is that? 2/10, hundredths, thousandths, 10,000ths, 2/10,000ths or so of the right value, so to speak, which is pleasant that you can get some experimental closure, I guess, results on those values. And then again, with a confidence interval of 90%, we get and degrees of freedom and 15 degrees of freedom, we can compare the book value of 1.341 with that I've calculated with using only 16 terms of the expansion, and we get something that's fairly close, within 1,000th or 2,000th or so of the right value. And again, here's some more. So with a confidence interval of with 25 degrees of freedom and a confidence interval of 99%, we can see that maybe 16 terms is not nearly enough, and our error is actually increasing somewhat, 3/10 or so, and that's the fourth value I calculated. And then my fifth value, I wanted to increase the number of degrees of freedom, and again, as you increase the number of degrees of freedom to infinity, the distribution actually becomes a standard, a normal distribution. But at 29, which is an odd value for the degrees of freedom, and a 75% confidence interval, you can see that we're right on the money as far as we're quite precise as far as reflecting the book value. But again, this has some limitations, not least of which are for higher confidence intervals. When we try to increase the confidence interval to 99.9%, the book value is 5.893, and the calculated value is way off, 3.325. And so you would need more terms in order to get the kind of precision you want out of the sequence. But it's nice to know that there is an analytical formula for calculating these values, whereas the values in this table are generally calculated using something like Monte Carlo or using root finding algorithms or using optimization routines, other kinds of approximation routines. And what's nice is that these values can at least serve as the initializations to those algorithms if you wanted. And in that sense, you can get close to the correct value and then perform a root finding algorithm in order to increase that precision. You could use something like Newton's method or the Newton-Raphson method. There are a lot of them. So it's nice just to look at the various values and see that there's some experimental evidence that corroborates this method. So I want to look a little bit at these values, because if you plot them in a triangular fashion, and it's easy to see that they actually have some connections to some previously known sequences. In fact, the first column, 1, 7, 127, 4369, that actually comes from this sequence in the online encyclopedia for integer sequences, A002067. The diagonal terms, that's 3, 6, 630, etc., those come from A007019. And more interestingly, to actually take the row sums, the unsigned row sums, that would be 7 plus 3 equals 10, 127 plus 123 plus 30 equals 280, etc. That sequence comes from A025035, and then interestingly, the alternating row sum, that's 7 minus 3 equals 4, negative 127 plus 123 minus 30 equals negative 34, etc. That comes from the sequence A002105. And so perhaps down the line there's some hope that instead of employing this more complicated, though complete, method of Dominici, there's a closed form, one line, simple expression for generating these coefficients. And then in that sense, one would be able to obtain these values to an infinite precision, any precision one wanted. So that's something I sort of hold out hope for. But I'll just leave it on this page. This is sort of the meat of the program. Thank you very much for listening. Thank you for following. I hope this had been helpful for people who wonder about these sorts of things. I certainly had a fun time producing it. Thank you very much.